So the last session this morning will be related to hypothesis testing or alternatives. So the first talk is from Simon. So he's going to discuss hypothesis testing development.
Thank you, Michele and the organizers for inviting me. It's an honor to be presenting amongst such awesome speakers. I'm going to talk about some recent work using semi-parametric methods for inference, for spatial extent inference for imaging data. I'll give a little bit of a background because I think a lot of the audience is familiar with how we do inference in imaging data. This is spatial extent inference, so this is a statistical map for a test of a null hypothesis from a group level linear model. So this might be, we're looking for group differences in activation between two diagnostic groups, or maybe we're looking for age changes. And so at each location in the image, we have a hypothesis test. Can I point? Yeah. A hypothesis test for whether a parameter could be a multidimensional imaging parameter is equal to 0. And so in spatial extent inference, we threshold this image at a particular cluster forming threshold, CFT, and then we binarize these clusters and we perform inference on the spatial extent of the clusters that are above the cluster forming threshold. And so this table is a list of the clusters in descending order of their cluster size. So in this approach, the image, the statistical image, is viewed as a random field, and the cluster forming threshold is chosen such that the statistical value passes some threshold, such as 3.09, which would mean the p-value at that location is below 0.001. So then, using this approach, we then perform inference on the spatial extent of the clusters. So you define a new set of hypotheses, which I'm denoting here by E of C. So these are the extents of each cluster. The notation is a little bit messy, but the concept is pretty straightforward. Your null hypothesis is that the parameter is equal to 0 for all voxels in the image. So this is the global null hypothesis, that the image is unassociated with the outcome. And so you compute cluster adjusted p-values by just finding the probability that the maximum cluster size under this global null is larger than the observed cluster size that you have in your actual data. And so a critical feature of this is estimating the joint distribution of the image. So several recent studies have shown that, that there are unrealistic assumptions in classical spatial extent inference procedures that make smoothness assumptions about the correlation of the image. And these GRF approximations only work well under very restrictive assumptions. So here's a recent paper, this is 2017. And so each, let me see here. So each column here is a different hypothesis testing method, spatial extent inference method. And each row represents a different cluster forming threshold. And then the x-axis here is the type 1 error rate. And the black line is the nominal type 1 error rate. So you can see, using these methods, there's a high false positive rate pretty much across the board using these like classical GRF-based inference methods. And this is one of many papers on this topic. Dan Kessler has one in response to this 2016 Eklund paper that was in PNAS. So kind of across these studies, people have shown that a permutation procedure maintains the nominal family-wise error rate. So here's another study. This is from 2018. And so the top row is the classical GRF-based method. The cluster forming thresholds are colored in different colors here. So you can see again, this is a different type of data. So this is cortical thickness data, this is area, this is volume. but you can see that there's an inflated type 1 error rate for different types of smoothing kernels. And this permutation procedure that I mentioned is maintains pretty close to nominal type 1 error rates. One limitation of the permutation procedure, though, is that it requires the assumption of exchangeability. So it's not going to be able to accommodate multi-level models or heteroscedasticity. So our goal in this work was to develop an inference procedure that's appropriate for multi-level models. So why do we care about multi-level models? Pretty much all imaging data is a multi-level model. I'll give you an example. This is the data set I'm going to analyze today. This is a fractal NBAC task. So in this task, this is an fMRI task. There's 3 stimulus conditions. 0 back, the people just have to click when they're presented a stimulus. 1 back, they have to click when the stimulus is the same as what was shown on the previous slide. And then the 2 back, they have to click if the stimulus is the same as what was shown 2 slides previously. This is actually a very challenging condition. And so in this model, we have a time series that represents each of these stimulus conditions. So we model our imaging data, which is a spatiotemporal time series, as a function of the stimulus time series. So we have the stimulus time series for the 0 back condition, 1 back, and 2 back. And then we have the spatiotemporal error process. So this is a subject level model. We can estimate this for each subject. What we do at the group level is we set our outcome variable to be some particular parameter from this subject level model. So in this case, we're setting our group level model to be the difference between the 2 back condition and the 0 back condition. That's what I just said. So again, multi-level models are extremely common in neuroimaging. This is the NBAC data. Because it's a multi-level model, that means the variance of the image for each subject, it can potentially depend on the covariates xi. That means that your data are not exchangeable. In imaging, because you have this high-dimensional multivariate outcome, it can be even worse, because even if your covariance between 2 locations in the image is different for subjects, that also means you don't have exchangeability. Other examples of multi-level imaging data, all of these types can be analyzed with the methods I'm talking about today, but cerebral blood flow, cortical thickness, functional connectivity, all of these methods, you're applying some complex estimation procedure to estimate what these measures are from the raw MRI data. So here's an example from the NBAC data of heteroscedasticity. So what I've done here is just taken the lowest motion and highest motion individuals, so that's what you're looking at in the top 2 plots here, and just look at how the correlations between regions in the image differ between these groups. So what you can plainly see from this image is that in low motion individuals, there's less interhemispheric correlations, whereas in high motion individuals, on your right, there's greater connections due to the increased amount of noise in the image. And D prime, so this is a behavioral measure of in-scanner performance. What you can see here is greater interhemispheric connections in lower scoring individuals. So because the covariance differs between subjects, this implies that heteroscedasticity exists in the data, or non-exchangeability. Indeed, the entire field of functional connectivity is evidence that heteroscedasticity exists in our data because it's the study of how the correlations change between subjects. So our solution to this problem is a semi-parametric bootstrap joint spatial extent inference procedure. It can accommodate heteroscedasticity, multi-level models, and eventually longitudinal models. We use like a Huber-White style robust covariance estimate to estimate the spatial correlation in the image. And so I'll describe how the procedure works now. So the general idea is you fit this model, so we fit our subject images as a function of nuisance covariates, beta naught, our parameter of interest, so this is xi here would be our d prime, so task performance. And then you get these residual images too from your model. When you fit this model, you can include a weighting, so that, like in a weighted least squares kind of framework, and this can be used to downweight noisy observations. So after fitting this model, you can use these residuals, and you use the weighted residuals to estimate the covariance of your test statistic image. And so what we do that's different is that we use a sandwich covariance estimator, and so here's a little peanut butter jelly sandwich. I love this sandwich. I use it in all these talks now. So what we do after this is we use a bootstrap procedure, so that's where the name comes from, the bootstrap, to sample this image, and then we use the bootstrapped distribution of the max to compute cluster adjusted p-values. So how do you choose the subject weights for the VBJ procedure? So optimally, your weights are the inverse of the observation level variance. Of course, we don't know what the subject level variance is, so, here's a picture. So each subject has their own covariance due to the fact that these covariates can affect the covariance structure of the data. And so if you knew this, you would plug it in as your weighting image in estimating your weighted least squares model. If you don't know what the variance is, a pretty good estimator I found is just plugging in the inverse of in-scanner motion as the weight, and that seems to be pretty robust. The thing with, because you're using like Huber-White style covariance estimator, even if your weights are misspecified, you still get asymptotically accurate standard errors, so your inference is still valid. Here's some brief theoretical details, just because nobody will ever actually read them in the supplement of the paper, so I'm making you read them now. We can only find the distribution of this test statistic image when the parameter you're interested in is one-dimensional. Here's the sandwich again. This is like, so your covariance of the test statistics has this nice sandwich form, except now you have a sandwich covariance function, not a sandwich covariance matrix. And the weight function is involved in like the components of this sandwich covariance estimator, which I'm highlighting here. And there was lots of tedious math, and none of the results are really that intuitive, to be honest. So to go back to the NBAC data, we are looking at a subset of 1,000 subjects, image as part of the PMC. So this is work I did partially at Penn and Vanderbilt. So our goal here was to understand how activation associated with increasing working memory load is related to task performance. So in this model, we fit our 2 minus 0 back condition as a function of covariates that we're not interested in, and then beta is our covariate of interest, d prime is our measure of task performance. How am I with time?
Still have 7 minutes.
Oh, okay, cool. So our null hypothesis at location B is that this parameter describing the association between task performance and working memory load is equal to 0. So we want to assess the effect of heteroscedasticity on spatial extent inference method. So how do we do this? I kind of like this approach to doing it. So we want to generate a realistic model of heteroscedasticity, and we do this by bootstrapping from the real data. So in a subset of the 1,000 subjects, we fit the model where we model our the imaging data as a function of covariates, but then we use these flexible, unpenalized splines to model these other covariates. And then we get the residual term here, and we store that for all of the 1,000 subjects. A feature of this residual term is now the covariates, the real covariates like age and motion, can affect the heteroskedasticity of the data, covariance structure, but now they're independent of mean in our 1,000 subjects residuals, the residuals of our 1,000 subjects. That's what I just said here. So again, just to remind you, heteroskedasticity, or sorry, the fact that the correlation between subjects can change as a function of covariance means that heteroskedasticity exists in our data, and assumptions of the permutation procedure and classical GRF procedure are violated. So the intuition here is we treat the residuals from the 1,000 subjects as our true population under the null. And so in each simulation, we draw a bootstrap sample and fit the following model. So we fit the residuals that we bootstrapped from our collection of residual images as a function of these covariates, and then again, our covariate of interest here. But now we know the mean of all these parameters should be 0 because we've removed the effect of those covariates. And so what we'll do is perform the test that within each bootstrap simulation that the parameter is equal to 0 for the D prime covariate, and then I'm also going to show you the results for the motion covariate as well. And the methods I'll compare here are the GRF, permutation, PBJ, and SPBJ procedures. There's the same. Okay, so there's a lot of information on this slide, so I'll try and slowly walk you through it. So across the bottom here, these indicate the different procedures. GRF here is the classical GRF approach. Permutation, these are two different permutation procedures. The first is the classical permutation. The second is to try and deal with heteroskedasticity. Here, these are PBJ procedures, which I didn't describe here, but they're a parametric version of the SPBJ procedure. And, whoops, I'm trying to point here. The 1 indicates no weighting for the subjects. The motion indicates that the subjects are downweighted by the inverse of their motion. And then the S is the same thing, except with the semi-parametric procedure. The left column here is the cluster forming threshold of 0.01. This is the other is a higher or more stringent cluster forming threshold. Within these subcolumns, you have the nominal family-wise error rate that you're shooting for. And on the x-axis is the observed family-wise error rate. So for the test of the motion covariate, which is the top row, the GRF, classical GRF method has nearly 1 type 1 error rate. And the permutation and unweighted PBJ procedures have an increased type 1 error rate, which is due to their inability to account for the heteroskedasticity in the data. The robust methods, which I'm highlighting here, sometimes they perform badly in smaller samples, but as you expect, so this is, what I'm pointing out here is the SPBJ procedure without motion deweighting. So the covariance is not, without deweighting, you don't have a great estimate of the covariance, but as you see, as the sample size gets larger, as the theory says, you should approach that nominal type 1 error rate. So the cool thing about the simulation procedure, is that you can assess how the heteroskedasticity of a real covariate affects the data, and that's what the lower axis is. So this is the D prime covariate, that's the covariate of interest. Your GRF procedure still has quite a high type 1 error rate, but your other approaches are doing pretty well. So this kind of indicates that if you're using the permutation procedure, even though your assumption of homoskedasticity is violated, you're still getting pretty good type 1 error rates in a realistic covariate. I'm going to skip the power analysis because I'm short on time. So here, I ran the analysis in the actual NBAC dataset. I just chose a random subset of 200 subjects because we had a lot of power in this data in the full sample. So here's the results. Kind of just to summarize what's going on. the smaller the SPPJ procedure ended up having more power, and the reason is because it had larger clusters, so it has a little more signal to detect, I think, lower signal voxels in the image. So we produced an R package to, it's called TVJ, and this analysis software is available in that. And now, I think with the other tools in Neuroconductor, you can fully perform the full analysis pipeline for imaging data in a reproducible way in R. Future directions are going to try and move into stuff that Armin is going to talk about, which is building confidence sets for regions of the image where the effect size passes a certain threshold. I want to, of course, thank my collaborators on this work at Penn, Sean Garbett, who helped me work on the package, and we're currently working on a GUI for the package now. And of course, thank you for your time.
So we have time for a short question. No question? I guess everybody's so hungry, right? They sandwich make us hungry. So then we can everybody can ask questions maybe during lunch.
Yeah, that's cool.
So the last speaker of this morning is Armin. So he's going to talk about some alternatives to hypothesis testing.
It's on archive.
Okay, so I can
It's accepted.
okay, it's usually I can tweet like your result slides.
Yeah, I put everything on
Okay.
archive.
Okay.
Fine, man. Yeah, so I submitted reviews and wrote accepted once you submitted reviews. I did that like a month ago and haven't heard back. So. Yeah. I don't really know.
That would make me nervous.
Yeah.
You work with compounds and stuff too?
We haven't started working together yet, but we keep talking about, I think our areas are a little bit different, but I think some of the stuff that
Do you use the state
we've been talking about.
This one.
Switch to this.
Yeah, because that was part of this,
HDMI. No, HDMI.
pretty much just dissertation stuff, all this in Prince.
Yeah,
Jeffrey School of
So
Thought.
the
Yeah.
A didn't work.
And I think some of the stuff with the effect size circulating that getting into will be, will overlap a lot.
Yeah. So you want to try to
Your archive thing linked from your GitHub.
No, that would be.
Yeah, this one didn't work either.
Oh, you mean the paper?
Yeah. I don't think it. Okay.
It's like impossible.
I'm just like
archive.
yeah, it's like I'm out of characters. I
Something
like,
better yesterday,
and so I'm trying to figure out like I feel like the GitHub package is maybe more interesting.
Yeah,
Okay, now it's showing up. Great. Perfect. All right. Well, thank you for sticking around. And thank you. Well, I don't know what everybody's thanking Michele, but I want to thank him too. It's been a great conference, and very high level, and I've enjoyed each one of the presentations. Really, I've learned so much in each one of them. And thanks to Simon, so he has already set up this talk for me. He has already told us about the problems that there have been with testing in fMRI. And testing goes back a long time. That's been the paradigm for identifying activation in fMRI for the last 20 years, going back to Keith Worsley, the founder of this, especially using Gauss random field theory. And it's natural that the word come out of the way that psychological testing happened in the field. However, this is an observation that Tom Nichols made to me, which is that as we get into this area of big data and we have larger and larger number of subjects, it turns out that we can have more and more power to detect effects. And here's, for example, results from a paper from 2012. It's Gonzalez and Gonzalez Castillo. And so, for example, they did something where they just took 3 subjects, but they did 100 runs per subject. I don't know how they convinced these 3 subjects to sit down and do 100 runs of fMRI. Okay, just imagine that. And then they averaged the results across runs. And then what you see here is that as you increase the number of runs, essentially, as you accumulate more and more and more data, then you have more and more power to detect the activation. And essentially, at the end of the day, if you use a family-wise error rate correction of 0.05, which is the standard that is used, then you may detect activation in 80% of the brain for this particular task. If you use FDR, which is a little bit less conservative, you get even more. 99% of the brain is active. And this is, in a way, if you think about how the brain works, there's more and more evidence that really the entire brain is participating in the activities that we do. So this idea that there's particular areas of the brain that are related to specific tasks, that is true at the level of the visual cortex or perhaps the motor cortex, which are very specific tasks. When it comes to more complex processing, then the entire brain is involved, like as we've seen with the basic networks and everything else. And therefore, just detecting activation is not enough. Same thing we will start to see with enough large sample sizes. So when we do second level analysis, let's say, for example, in these large cohorts, the ABCD study UCSD has just finished collecting data for 11,000 kids. And we've heard about the UK Biobank, which also has 20,000 subjects with fMRI scans, and it's still growing. And so for group effect, basically, again, same message. You'll find that large parts of the brain, if not the entire brain, will be active in these tasks. And something that I learned as a student already from the beginning is that statistical significance, well, of course, it's a function of the effect size, but mostly it's a function of your sample size. With a large enough sample size, eventually you would reject the null. Right? So is that meaningful? And so the solution, well, one thing that I heard as a student again was, well, then you can just estimate the effect, and that will be more meaningful, perhaps. Or you can go Bayesian. That's another possibility. Which I'm not going to touch. In just like univariate situations, you may just produce a point estimate and produce confidence intervals. Then my idea here was, if we're interested in finding these regions or mapping the brain and finding regions where the activation is happening, then can we estimate these clusters? Just estimate these regions, find where they are, and then put confidence sets around them. So what I'm going to do is propose an extension of the basic idea of confidence intervals into spatial sets. And this is what the sets may look like, that I'm proposing to do. Because activation may be everywhere in the brain, then let's set a particular threshold. Suppose we're looking for regions in the brain where the bold signal, the percentage bold signal, is greater than a certain threshold. In this case, suppose 0.5%. So we're looking for these particular places where there's more activation than usual. And then I'm going to produce these 3 sets in these 3 colors. The yellow set, which includes the red set. So think of the red being on top of the yellow and being on top of the blue. Okay, so think about it that way. So the yellow sets, we include the red. These are my point estimates of where we think that the percentage bold is greater than 0.5%. So these are regions where we think the activation is. And then we have the red set and the blue set. What is the red set? The red set is what I call the inner set. Oh, sorry. The inner set is like a lower bound or an inner bound. These are the regions. The red regions are the sets where we're pretty sure the activation is. And then there's the blue sets. The blue sets are like an outer bound. And the activation, we're thinking that with high probability that they may be as large as the blue set, meaning that every voxel that is outside the blue set would most likely not be active. So this is giving me just a range of how accurate my estimation may be. So how we define these formally then? The idea is that suppose we're trying to estimate now more abstractly with me for a moment, estimate a mu function. So mu is the target function. That's the activity, the bold response that we're trying to estimate. And we have an estimator mu hat of it. And I'm going to define then formally this way, as the excursion set. So AC is going to be the target set. That's what I'm trying to estimate. So these are the location S in the search region, big S, where mu of S is greater than C. So think of percentage ball being greater than 0.5%. Mu of S greater than C. And I'm going to estimate it by simply a point estimate. If I have an estimator mu hat, then A hat consists of all the voxels or locations S, where mu hat is greater than little c. So that's a yellow set. That's it, it's just a point estimate. Now what is the red and the blue? So I want to come up with some inner set A hat plus and A hat minus. The colors I change here, but this is the red and this is like the blue, right? The inner set and the outer set in such a way that these two sets bound the set AC with high probability. So that the red set will be included in the true set, and then the blue set will include the true set, and all these things will happen with a high probability. That's what I'm trying to do. So how I'm going to do this? So the plan for the next just 10 minutes, whatever time I have, just tell something about the theory and the algorithm, and so back to the data. So we call these coverage probability excursion sets, COPE sets. And how do we define them? The idea is quite simple. A hat plus is still an excursion set. Let's say it over here, where I'm going to take mu hat greater than C, but instead of just taking the level C, I'm going to take the level a little bit higher, plus some delta. So here's a cartoon that explains it. So I'm looking here at our image from the side. So this pink curve is mu hat, right here. This is the level C. So when I threshold mu hat at level C, I get the yellow set, right there. If I go a little bit higher, I get something a little bit smaller. So that's going to be my red set, C, at the level C plus delta. And if I go lower, I get something a little bit higher. That's the blue set, which is the outer set. And then once you project into the image, this is what it's going to look like, right? So the red inside the yellow, inside the blue. So these sets are nested. And that's the construction, so it's an easy construction. The question now is basically just how do we identify these deltas? So how much to go up and down so that we can capture, we can bound it by the right probability. And this delta is going to be a multiple of the standard deviation. Clearly. And so I'm going to give you the theoretical result first, and the conditions, there's very precise conditions for the result to hold, but to summarize it, I need the domain to be compact, and I need the signal mu to be continuous, and I need mu hat to have a central limit theorem, because I'm going to have an asymptotic result. That's a central limit theorem, right there. For example, mu hat could be an average, and then you have a central limit theorem that converges to a Gaussian random field. So that's what I need. And this is the result under those conditions. Then we have a result that proves that the probability of inclusion, which is what I wanted to obtain, that has a limit as n increases, as we get more and more and more samples. And the limit is interesting. So the limit is the probability that, or it's essentially the distribution function of the maximum of that limiting Gaussian random field, G. So G is the limiting Gaussian random field of my mu hat. And it's a distribution function of G, of the maximum of G, where? Over the boundary. So that's what I'm trying to digest here. So this is the probability that the maximum of G over the boundary is less or equal to A. Why over the boundary? I'll tell you just briefly. Because if we go back to this picture, here's what happens. I didn't draw the mu, but mu is somewhere underneath here, and the true set should be somewhere close to the yellow set, right? As n increases, mu hat is getting closer to mu, and therefore the yellow set is getting closer to the truth. Now, mu hat may have some variability, right? So it may be crossing this level in places that it shouldn't because of noise. And that's going to produce errors in the inclusion. But as my sample size increases and mu hat converges to mu, then it's less and less likely that there will be some errors in the inclusion right here. So most of the errors will be simply because there's something shifting here at the boundary. That's where most of the errors are going to be. And that's why the result says that eventually the probability of an error has to do with the distribution of the maximum at the boundary. So that was an interesting result that we found, but that tells us a way to choose our quantum, A. now, because if we construct our sets in this way, as plus minus some factors times the standard deviation, then what we need is just to find the distribution of this maximum of the limiting Gaussian field. And then if we can set, so if we have this distribution, then all we need to do is just set this quantile A so that this probability will be less than alpha, because this is the probability of error right here. So as long as you get this distribution, we set the quantile, and that will guarantee then that the inclusion will have a good probability of these 1 minus alpha. So that is the procedure. So what is the challenge that's remaining is, well, just to find the distribution of the maximum over the boundary. So that's all we need to do. An additional problem that, well, the boundary is not known either. The boundary is actually easy to solve. We can use a plug-in estimator because we have a hat, so we can just take the boundary of a hat to be a plug-in estimator. And what we're missing though is the distribution of maximum. And that's harder because we don't know what this limiting field is. However, okay, before I tell you how that is, I can show you how this applies to fMRI. This is the classical Vauxhall-Weiss linear regression model. So y is equal to xb plus epsilon, whereas in the typical fMRI, y is a vector of. So this is an example for a single subject analysis. We can also do it for a second level analysis. It will be similar. So y is observations, x is the design matrix, b is our coefficient, then we have error, etc. And the error here is a vector, right? So the vector error has two types of correlations in it. It has temporal correlation and a spatial correlation. So we're allowed here for both. So there's a temporal correlation matrix gamma of S, which may be changing over space, and that's fine because it can be estimated from the data. And then it has a spatial autocorrelation function right there too. And the way you would fit it is by using generalized z-squares. So in general, the way we typically do generalized z-squares is that this matrix gamma can be estimated simply from the time series if there's correlation in there. So this is the most efficient way to do it. And theta Vauxhall-Weiss, and then you got an estimate of b hat. And typically we'll want to estimate some kind of contrast. So if we have a vector b in terms of all covariate, then W transpose b will be a contrast, which is our target function mu. So in this case, mu will be what we're trying to do. And mu hat will be W transpose b hat. So I need to convince you now that this model satisfies the assumptions of my theorem, and that's theorem number 2, which is that under appropriate boundedness conditions of x, well, it's a theorem, right? So I need to have some conditions on x as n increases, and that led us to go into some classical papers by Peter Bickel in the 70s to figure out when is that linear regression estimators are consistent, and the theory is there. It's actually more complicated than you would think. I mean, we always use linear regression, always assume that the coefficients. I teach a course in linear regression, and I would wish I could explain to them why linear regression estimates converge. It's not so easy to explain, but they do. At least if the matrix X is bounded, and at least fMRI, I would say design matrices are bounded, and they're nicely. So under those conditions, then mu hat satisfies the central limit theorem that I need. And what is nice about this is that the limiting field, in this case, actually has the same autocorrelation function as the noise. And that's important. So if you start with noise in your fMRI image, a certain spatial autocorrelation, then that correlation will be preserved once you calculate your z-scores. Not z-scores, I mean, it will be the same limiting distribution that we need. And remember that we need the distribution of the maximum of this limiting Gaussian field. So I don't know what the limiting Gaussian field is, but I know that it has the same spatial autocorrelation as the noise in fMRI. So that's important. I'll tell you in a moment why. Therefore, if I have the CLT, and if everything is smooth, then I can apply this theorem to the fMRI set. How do we actually do this? All right. So I just told you that the spatial autocorrelation function is the same as in the noise. Do I have access to the noise in fMRI? No, but I have access to the residuals. And the residuals is actually the closest thing that I have. But I can produce these residuals R, which are y minus x beta hat. And the idea we're going to use here is a wild bootstrap in order to access the distribution of the maximum. I don't need the actual field, but I have these residuals. So what do I need to do? Well, I need to produce some field G of S that will be similar to the G of S that I'm actually looking for. So in this case, I'm going to call this G tilde. And I'm going to produce this by taking a linear combination of my residuals multiplied by these Gaussian multipliers. Why do I do this? Because multiplying by these Gaussians, then I'm producing a Gaussian field. Right? That's the first thing I need. And second, there's a heuristic argument, which I wrote here at the bottom, which shows that condition on the data, the spatial autocorrelation of this process G tilde is exactly the same as the empirical autocorrelation of the residuals. So I'm showing here is that this covariance, spatial covariance, is the same as this one. And that's good because what you see here at the bottom, this is, well, as an estimator of the total autocorrelation function, it's actually pretty bad because you can't really estimate the entire autocorrelation function. But it is 5 minutes, great, no problem. But it is close enough in the sense that producing the G tilde will have, well, G tilde by itself has a similar correlation structure, but the important thing is that what I care about is the maximum. And so this will be enough in order to produce the maximum. So if I produce now very many instances of G tilde and take the maximum over those, distribution of the maximum will be close to the distribution of maximum that I actually need. And that's exactly what the algorithm is. So here it is. So you fit the linear model, number one, take the B hat, take the residuals, need to standardize them so that we have mean zero and variance 1. And then we apply this multiply bootstrap. We take many realizations, take the distribution of the maximum, find the quantile empirically, and construct your probe sets. And that's what it is. So in terms of time, we did several simulations with different signals, different types of noise. And the important thing is not the results of the simulation so much, but with this procedure, because we're using this multiply bootstrap, this works for under heteroscedasticity, meaning that the variance function may be completely different over space. Even the process itself, autocorrelation, can be completely non-stationary. It doesn't have to be the same in different parts of the image because it's all captured by the bootstrap, right? It's all captured there. So these are different noise conditions, and yes, the coverage is near the nominals and increases. We even tried this just for a solution. Because we're using a continuous approximation in discrete space, so of course the results will get better as the resolution increases, but at least it comes from above. So if we have discretization of the space, then the coverage will be a little higher, but it does converge. And well, I can almost finish up. Let me see, yeah. Going back to the data and just comparing again what the results would look like if you do testing versus if you do this estimation approach. So in the classical inference which is on the left, here we have data from the UK Biobank, 1,000 and 8,500 subjects. And this is what happens. So when you have a large number of subjects and you do a group analysis, you get large regions of the brain that are active on that particular task. And so it's hard to localize, right? This is, maybe it reminds me of what Martin was presenting before, where you have too much activation. How do you concentrate? So here trying to have an honest solution to the problem. And this may be true, that really all these regions are active, but you try to identify the ones that are maybe the ones that are more representative of where the activation really is. So if you threshold at a percentage ball of 0.2%, again we get these regions in red. The yellow ones are the point estimate, red inside, blue inside. And what we want to show here is that as we increase the number of subjects, then we do have convergence. So the blue and red sets are being tighter around the estimate. And by the time you get to this number of subjects, I think the regions are pretty well defined. 1 minute. So main message, construct confidence regions. So forget about testing, that's my message. Just forget about multiple testing, just estimate your sets. And the references are, so we have 2 papers on this so far. The paper with the theory is a JASA paper, 2018. Actually, that was used that was motivated by a climate application in 2D, but then we transferred it to 3D and fMRI, and that's a paper that is under review on your image right now, but right now it's still available in bioRxiv. And we have an R package. That's for the 2D situation, and for 3D, it's MATLAB code that one gives me to package of properties. All right, thank you very much.
One of your last slides, could you just go back to your
One back?
results
Yeah.
that you shared? The UK.
Yeah.
So, maybe Martin should close his ears. It seems like if you threshold it to just the yellow part, it seems like you get your results.
You get what?
Right? If we just threshold it enough to just get the yellow activation on this image, it seems like you can get your results, right? Or it's very similar. The yellow activations on the left side kind of matches, yeah, it kind of matches with even the tiny blobs on inside.
Yes.
Right?
Yes. That's a very good point. The images on the left, these are the t-statistics, right?
Yeah.
And the t-statistics are proportional to the mean function underneath. But it's a mean function divided by standard deviation. So if the standard deviation is constant across the brain, then dividing by that constant would be just give you something that is proportional, right? The difference is that here we're thresholding the mean function, while here we're thresholding this statistic, which is proportional to the effect size. So the differences are going to start to show up when you have heteroscedasticity, where the variance function is different. And in fact, one of the extensions that we're working on right now is to try to do this for the effect.